Alright, in this video tutorial we're going to talk about normal distribution. We're gonna see how we can generate a normal curve in R for a variable that follows normal distribution, and how we can find the probabilities from the normal distribution using several examples. As you know, a normal curve can be defined by only two parameters. So if we know the mean and also the standard deviation for a variable that follows normal distribution, we can just plug in the values, the mean and also sigma or standard deviation or S, into this formula for different values for different x's, and then we can have the y, the height for any given point on the normal distribution, because the other values are just constant, right? So if we just have mean and a standard deviation, we can plug in the values into this formula, and then we can measure y, which is the height in the normal curve, okay, for any given point. And the normal curve is also known as probability density function, or PDF. We don't have to worry about this formula because R has functions to calculate it for any given point. So let's see some examples to make it clear. Before we start writing the codes, it's better to create a comment that that shows the purpose of this code. Okay, so the purpose of this code is to learn normal curve and probabilities from the normal curve. Okay, so in next time when we refer to this code, we can understand the purpose of writing this code. Let's say we want to create a standard normal curve, and as you know, a standard normal curve has mean of 0 and a standard deviation of, or ST, of 1, right? So we want to create a standard normal curve in our environment, okay? Between -3 to +3, which is 3 standard deviation above mean and 3 standard deviation below mean, okay? So to create a sequence, if you remember, we use seq function, and then from -3 to +3, okay, and then by, which shows the steps, for example, by this value. Okay, so when you click run, it will create the values from -3 to +3. So actually we are producing the x, right? And so I save this into an object with the name of x. Okay, so if you click on run, now we will have the x here running from -3 to +3, and the steps are 0.01. The next step is to use denorm command to create the y, which is the height of normal for each of these values, right? For each of these values, I'm going to generate the y, which is actually, so we have x's, we have mean, and also the standard deviation. So I'm gonna generate y for it. So we can use this formula, but R has a function that makes our life so much easier. So it's called denorm function, and for denorm function, the first input is our data, our x, right? Which is this vector, these values. And then the second one is the mean of the data. The mean was 0 because it's a standard normal, and the standard deviation is 1. And the output will be saved in an object called y. So what it does is, for each of these values we are generating y, right? So for example, we put the value -3 here, we have mu, we have a standard deviation, everything else is, and also a standard deviation here, so everything else is constant, so we can calculate y. but this can be done for each of these values, right? So that's x and y. So we have x, we have y. So the last step is to just plot y versus x, right? So we have x here, we have y here, and then when we plot x versus y, so it will shows us the normal distribution. So the value of our x are between -3 to +3. And if you remember, the reason that we use -3 to +3 is 3 standard deviation below mean and 3 standard deviation above mean, which is 3 standard deviation above 0 and above below 0, right? So that's how we can generate a normal distribution. Let's summarize what we did. We first generated the x from -3 to +3 by steps of 0.01 and using the sequence command, and then we calculate the height of normal distribution for each of these x using denorm command, which is actually to plug in the x values into the formula, the normal formula. So we have x and y, and finally we plotted y versus x, and then we got the normal curve. Okay, so now let's make some changes on this plot to make it look much nicer. So we want to, so these are actually points. If you, for example, reduce the number of points here, if you increase the steps, actually we will see the points. So these are actually points, okay? For each x between -3 and +3, we calculated y and then we plot them. So we have points, right? What we can do is we can connect these data points using the line, and we should, in this case, we should use a argument with the name of type. Okay, so how to connect these points using type, and then set this as L, which shows, so the points should be connected with line. Okay, so don't forget that this is L, and don't forget that put that in the quotation, and then when you click run, we will have this distribution, we will have this normal curve. And also you can change the color to blue. Okay, so again, so you know that the argument is COL and then blue. We can limit the x-axis from -3 to +3, which already has been done. So you can, for example, XLIM, you can limit the values. You can use, for example, -4 to +4, but most of the data, 99.7% of the data are between -3 and +3. So if you use -4, for example, to +4, so between -3 and -4 is almost 0. Okay, so if we run it again, we can see that between -3 and -4 is almost 0, right? That's why we use -3. So it can be from -infinity to +infinity, but the most of the data is 3 standard deviation below and 3 standard deviation above the mean. So another thing is we can add a title to this curve. So using the main command, we can type x. So x means any parameter that follows normal distribution. Okay, x follows, so this tilde, normal distribution with the mean of 0 and the standard deviation of 1. Okay, that's a standard normal. So x follows normal distribution. So for example, this is age follows normal distribution with the mean of 0 and a standard deviation of 1. And we can also increase the width of this line using LWD command, line width to, for example, to 2. Okay, so you can see the line width will increase. Why it is between -4 and +4? Because we have to run the entire code here, and now it's between -3 and +. So the process that we use to generate the normal curve can be done for any variable that follows normal distribution. It's not necessarily for the standard normal curve. Okay, so let's say you have a variable. Okay, so create normal curve. So create normal curve, or any normal curve. You can use the same process. So let's say you have a normal variable that follows normal distribution. For example, weight. Okay, so weight. Oh, sorry. So your the weight maybe follows the normal distribution with the mean of, I don't know, 50 kilogram and a standard deviation of 5 kilogram. Okay, that's a hypothetical example. We're gonna create the curve, the normal curve for these people because it follows normal distribution. Again, we can use this formula. We can use the sequence and then denorm and then the plot them. But sequence should start from 3 standard deviation below the mean. Okay, so let me call this mean. So 3 standard deviation below the mean means 50 minus 3 standard deviation, right, which gives us 35. And 3 standard deviation above the means 50 plus 3 standard deviation, 3 standard deviation, right, which is 65. Okay, so these are not the codes. I just wanted to show you that the values starts from the sequence starts from 35 to 65. Okay, or it can be between 30 25, or it can, but it should be at least from 35 to 65. So so we create this sequence. Let me copy this. Okay, so the sequence should be from 35 to 65. Steps are 0.1 denorm, and the mean is 50, right? The standard deviation is 5. Plot x, y against x, type L, connect them with line, color blue, and main. So we're gonna add a title that the mean is 50 and the standard deviation is 5, right? And line width is 2. So the next step is just to select this bunch of codes and then click run. So now we have this normal curve that the mean is in the center, right? Mu, or mean. Mean is 50 and the standard deviation is 5. So 1 standard, 2 standard, 3 standard deviation. That's why it finishes at 65, which is close to 0. And also 1 standard, 2 standard, 3 standard. We can say that almost 99.7% of the data of all of the measurements will be within 3 standard deviation, below and above the mean. Okay, so that's how we can create the normal distribution if we have the mean and a standard deviation. Okay, so we have standard deviation and we have mean. We can generate the normal distribution. So these are for each value that we generated. These are the values of the sequence that we generated. So you can also, another thing is that you can also add a vertical line here. So using the AB line, this is outside of the plot. Okay, using the AB line command, and you can add a vertical V at the mean, okay, which is 50. Okay, so we can run this code and we'll add a line here, or you can change the color of it, for example, to red. Okay, and run. So let's see what happens if I change the mean and a standard deviation. Okay, so this is our data, and it starts from, for example, it can start from 30, so it doesn't really matter. Okay, or we can finish at 80 or 70. Okay, because the values above, outside of this 35 to 65 is almost zero. Okay, so it can be from negative infinity to positive infinity. They are almost zero. So you can see in this case the values are almost zero, the y value. But let me change the mean and see what happens to this curve. Okay, and also change the standard deviation. Instead of having a mean that is 50, I use 55. Okay, and everything else is the same. So sequence runs from this value to this value. Standard deviation is 5, and AB line is 55, and everything else is like this. So just remember the shape. Okay, so when I run the entire of this code, so this shape doesn't really change. Okay, the shape doesn't change. The only thing that we see is the shift in the location of the center. So the normal distribution shifts to the right. Okay, so because it's the mean is 55. If the mean was 45, the normal distribution will shift to the left part of this plot, right? When you change the mean or mu, it actually, we won't see any changes in the shape. The shape will be preserved, but the location of the center will shift. There will be a shift in the location of the center. Okay, so this time I'm going to change the standard deviation from 5 to 1 and see what will happen to the shape. So standard deviation is 5 and the shape is like this. And I'm gonna change the standard deviation, so it was between 35 and 65, right? So let me run this code. So let's change the standard deviation from 5 to 1, and also in the main. It doesn't really have any effect on the result, but let me change this. So if I change the standard deviation, just notice what will happen to the shape of the normal distribution. So you can see if you use a smaller standard deviation, distribution will cluster around the mean. Okay, so because this means that most of our measurements of weights are closer to the mean of weight, okay, or 50 kilogram. Okay, because the standard deviation, because if you remember, the standard deviation shows the spread of data around the mean. So less standard deviation means less spread of the data around the mean. Okay, that's why the values are closer to the mean, and also the height will increase. Okay, compared to the previous one, the values increased. So remember this 0.3, right? So the previous option was 5. So now the values, that the height of the normal distribution kind of shortened, right? Decreased. So the next step is, so now I'm going to increase the standard deviation. So instead of having 5, I'm gonna have 10 as a standard deviation. And to better see the result, let me change the sequence running from 10 to 100. But the values, we know that most of them are 0, right? Between outside of the 35 to 65 will be 0. So it won't have any effect on the result. This time I'm going to use, instead of 5, I'm going to use 7, okay? So, and see what will happen to the shape of the distribution. And here I'm going to change the title. So let's select the entire code, and then Just notice what will happen to the shape of the normal curve. So we can see that when we increase the standard deviation, distribution will spread out, okay, which means that the measurements of weights are far from the mean, are far from the 50 kilogram, because again, a standard deviation is deviation of each individual measurements from the mean. Okay, so when you increase the standard deviation, so we will have more more deviation from the mean. Okay, so the values is spread out, they're not close to mean. So when we have smaller standard deviation, values will be closer to mean, so we will have a spike. But in this case, when you increase the standard deviation, your distribution will spread out. Area under the normal curve to the left of any given value shows the probability, right, and can be calculated using pnorm command. So let's see an example. For example, let's say you have, so here we have probabilities from normal distribution, normal curve, which corresponds to the area under the normal curve to the left side of the any given value. So let's say you have a standard normal distribution. We want to find the area to the left of the value of 0. Okay, so we use pnorm, and what value you want to calculate the area for it. So we want to calculate the area that is to the left of the value of 0. So let's say, so let me create that for you to better understand. So because this is a standard normal curve, I can copy that here, and then so this is our curve. I'm going to measure the area below the 0, below the value of 0. Okay, so we use pnorm command. It's very simple. So pnorm, and what value? 0, and the mean is 0, and standard deviation is 1. Okay, and you can see the result is half, right? So the probability that a value is less than 0 is half, which we already know that because the entire thing is 1, and this is a symmetric curve, so here will be half and here will be half, right? So but sometimes it can be difficult, it's not always easy. For example, the probability of the value less than 0.24, okay, in that case you can't say, just look at the shape and can't say the result. So it should be definitely greater than half, right, because it's here and it's greater than, the area will be greater than half, right? So it's 59%, right? And so that's how we can calculate the probability from the normal distribution. And again, from the standard normal distribution, and again, it's not necessarily a standard normal distribution, it can be any normal distribution, so with the mean of anything and the standard deviation of anything. So what we're going to do is that now we're going to shade this area between -3 to 0.24. Okay, so let's create a comment, shade the area under curve. So first of all, we have to create a sequence running from -3 to the value that we want, 20.24. So seq from -3 to 0.24 and by 0.1. And then we save it in an object with the x. And also we use denorm to measure the y, and the input value is this sequence that we created, and the mean, which is 0, and a standard deviation of 1, and we save this in another object y, And here we should use polygon command. Okay, so it creates a polygon running from -3 to 0.24 for x, and for y is 0 and 0, because the other values are connected to the curve. Okay, so the polygon, because the values, there are more than one values, we have to use C command between -3 all of the x's to 0.24. Okay, so I'm gonna shade this area -3 to 0.24 for x, and also for y is 0, y, and 0, and then change the color of it to red. I think this should work. Yes, so that's the value 0.24, and this is the area below the 0.24. So for example, if you have if you want to measure the area between -3 and so the p norm, for example, I want to measure the probability that the value is less than 0.75 or 1.5. Okay, so we use p norm, and the probability, because this value 1.5 is almost 90%. Okay, so it'd be a large area, and then we create, I'm going to shade the area less than 1.5. So we start from -3 to 1.5 by this value. The distribution is standard normal distribution, but it can be any normal distribution, and x's are between -3 and 1.5, and the y is always 0 and 0. So now if I run this bunch of codes, so we will have this shaded area. So let's solve two real-world problems. Let's say systolic blood pressure for adults has a normal distribution with the mean of 130 and standard deviation of 35. Okay, so example number 1. So systolic blood pressure has a normal distribution with the mean of 130 and the standard deviation of 35. Okay, and what we're going to do is that first of all we're going to create the normal distribution curve, and then find the probabilities that a person has a systolic blood pressure for different values. Okay, so first of all create a normal curve. So for normal curve, you know that, so we have to find a sequence number starting and ending values, which is mean plus and minus 3 times of the standard deviation, right? So sequence should start from 130 minus 3 times of standard deviation, and 130 plus 3 times of the standard deviation, right? And then by 0.1. So that's the sequence that we create, and then store it in the variable x. And after that we use denorm formula. So if you remember how we generated this standard normal curve, we use denorm and then we plot the results, y versus x, right? So then denorm of the x, and the mean is 130 and the standard deviation is 35, and plot x against y, color blue, mean normal of 130 and the standard deviation of 35. Okay, so that's how we can generate the normal curve. So the normal curve, you can see, so the values are between this value and this value. So that's the normal curve. And now we're going to measure the probability that a person has a systolic blood pressure less than 90, for example. So part A of the question is the probability a person has a SBP, systolic blood pressure, less than 90. Okay, so we use P norm, right? So the P norm, what value? 90. And what is the mean? The mean is 130 and ST is 35. So it's very simple and straightforward. So that's the probability that a person has a standard deviation, has the systolic blood pressure of the 90 or less. Okay, because this gives us only the left part of it. So it's the value is almost here, and the probability is the area under here, right? So we can also shade this area. Okay, I just copy that. And then shade the area. Shade the area under the curve. So running from this value. What is this value? Let me measure that temporarily. It's 25. Running from 25, and how about the plus? Is 235. Okay. So sequence is from 25 to 235 by 0.1 d norm. The mean is 130 and a standard deviation is 35, and we're going to measure the area under the curve that the values are between this value, the minimum, which is 25, until 90. Okay, SPP less than 90. Y is 0 always, and then so sequence from 25 to, sorry, it should be to 90, right? So we have to run this first. Okay. So first we have to create the normal again, and then so that's the area below this, and it's 0.12. It's 12%. Okay. So the second part is the probability that a person has a systolic blood pressure above 150. Okay, I'm going to measure the probability that a person under the normal distribution with the mean of 130 and a standard deviation of 35, what is the probability that the person has a standard the SPP above 150? Just notice that the P norm is only for the only calculates the area to the left of this normal curve. So how about the right? So I'm gonna have the values above this value, right? So in that case, we can use the P norm, okay, for the values of 150. But so this is this probability, but we know that the total area is 1. So 1 minus this value gives us the probability. Okay, so that's the probability, which is 0.28 or 28%. So it's the probability that a person has a systolic blood pressure above 150 is 28%. And also you can shade the area under the curve. So you can easily shade the area under the curve. So the sequence, so I'm going to shade the area above 150. So the sequence starts from 150 to the last value, which is 235, I think, right? So the sequence, I think it was 235. Yeah, so sequences start from 150 to 235, and this is the steps. And also denorm, the mean is 130 to SD is 35, right? The C, the values should be between 150 and 235 for the X. For the Y is 0. Okay, so we can run this, but I think it's it will still keeps this part, so we have to run this part and then run this part. So that's the area above 150. So, and finally, how we can calculate the probability systolic blood pressure is between two numbers. For example, between 100 and 150. Okay, so probability that SBP is greater than 100 and less than 150. So in that case, we need to if we use the p norm, it gives us this area, right, below 150. And also if we use p norm for 100, we will have this value. So if I do the difference between the area below 150 minus area below 100, so we will have the area here, right? So what I'm gonna do is I'm gonna use the p norm, okay, and then the value of 150, mean of 130, and ST of 35 minus p norm of the values are below 100, right? 100, mean, 130, and ST of 35. That's 52%. Okay, so and also you can shade the area under the curve. Shade the area under the curve. I'm going to have the values between 100 and 150 by 0.1, denorm 130, 35 is okay. The values are between 100 and 150, and everything looks good. So let me just run this curve and then between 100 and 150. So now you can export the values, export these plots into the JPEG or PDF or any other formats for images, and then use it for your purpose.